This is a wave tutorial presented by DSC Charles VB. Hello, welcome to a new tutorial presented by DSC Charles VB. This tutorial will allow you to see waves. Now, before we start with waves, you need to visualize a small introduction in waves. And that introduction is going to tell us that waves is the main thing which is involved in the transmission of signals. When I'm hearing a phone call from someone, I'm just hearing signals which are emitted via waves from one phone into my phone at home. So this is a brief introduction to waves. So wave is just a function, it is just a signal which is used in transmitting energy from one point to another. So now in this tutorial, we're going to visualize different quantities. The first quantity I'm going to visualize are going to be the quantities according or due to the particles of the waves. The second quantity we're going to visualize are going to be the quantities due to the wave itself. The quantities according to the particles of the waves are going to be the displacement, the velocity, and the acceleration. While the quantities involved with the wave itself are going to be the amplitude, the frequency, the wavelength, the speed of the wave, the energy transfer, and the power transferred of the wave. So now let's define a wave. A wave is defined as a periodic disturbance / a signal which transfer energy from one point to another without a linear transfer of particles forming the medium transferring the wave. So it transfer energy from one point to another without the transfer of the particles which are going to cause a vibration of these waves. Now, types of wave. Now, our whole chapter is going to be based on three types of this mode of classification of wave. The types of wave are going to come from the different classifications of wave. So now these are the different mode of classification of wave. Number one is the mode of vibration. Number two is energy transfer, and number three is medium of propagation. And all of them are going to be described with respect to their definition, their diagram, the formulae or quantities involved in each classification, and the specific explanations. So now let's start the classification according to mode of vibration. When classifying a wave according to mode of vibration, there are two main types of wave: the transverse wave and longitudinal waves. Transverse waves are waves whose direction of motion are perpendicular to the direction in which the particle vibrates, as shown here. You see that the particle are going to vibrate here, while the direction of motion of the wave is going to be perpendicularly to the direction of vibration of the particle. So thus they are called transverse wave. So now let's visualize the formula involved. So this is a diagram for transverse wave. The formula involved now in transverse wave. Transverse wave, this wave here, we know that this form of equation is going to be a sine curve. This is why we just write y is equals to sine theta. But realize that this graph is going to be the displacement against the time graph. So we don't have y, or which is displacement against time. So we have to place a time here. In order for us to have a time here, we are supposed to use theta is equals to omega t, because we know that omega is equals to the theta, the differentiation of the theta with respect to time. So now in order for us to place the time as being a variable of y, we are going to say that sine omega t, y is equals to sine omega t. Now in this case here, we realize that there is a certain amplitude a. So this function is going to be of form y is equals to a sine theta. So lastly, we can say now that the displacement function is going to be written as y is equals to a sine theta as such here. So now that's the displacement function of most wave. So now after having the displacement function, we can have now the velocity function. The velocity function of the particles of the medium is going to be formed from the differentiation of the displacement with respect to time. This is a formula from classical mechanics, but we know that y is equal to a sine omega t. So we are going to differentiate it with function of functions. So we are going to have vy is equal to omega a cos omega t. So now this is the first formula for the velocity of the particles which are moving. So now let's visualize now another formula for the velocity of particles, and this formula is going to come from sine squared theta plus cos squared theta equals to 1. So we initially had omega a cos omega t. So from this formula we see that cos theta is going to be equal to the square root of 1 minus sine squared theta, but theta is equal to omega t. You substitute, you are going to have this. Also, we know that y is equal to a sine omega t. It implies that omega t is equal to y all over a. We can substitute back in this equation and say that cos omega t is equal to the square root of 1 minus y all over a squared. So now when we are going to substitute now in the formula for the velocity above here, we are going to have this new formula omega a, the square root of 1 minus into y all over a all squared. When we expatiate, we are going to have the velocity of y is equal to omega a, the square root of a squared minus y squared. So now let's visualize now the implication of this formula. What does this formula implies? It implies that you see that the maximal velocity here is going to be omega a squared, and the omega a squared is formed when the displacement is going to be 0. So what does it imply? It implies that maximal velocity of a particle is going to be attained once the particles are going to be at their equilibrium position. So that's the meaning. Maximal velocity is going to be attained once the particles are going to be at their equilibrium position. So at this position here, the particles which are at this position here have the maximal velocity. They have their maximal velocity once they are in equilibrium position, or the angle theta is 0. So now let's find out for acceleration vector. The acceleration from classical mechanics is found from the differentiation of velocity with respect to time. But we know that velocity is equal to omega a cos omega t. When we substitute, we are going to differentiate and have acceleration equals to negative omega squared a sine omega t. Now we see that a sine omega t was initially y, so it implies that the acceleration is going to be equal to negative omega squared y. Now, but this formula is a good formula which is typical in simple harmonic motion. So this is the formula which is used in the definition of simple harmonic motion. So waves are moving with a simple harmonic motion. And let's have the definition of simple harmonic motion. So the simple harmonic motion is defined as a motion where the acceleration is going to be directly proportional to y, and the acceleration vector is always going to point toward the direction of the equilibrium position. So we see that this definition of simple harmonic motion has two main parts. The first one is where acceleration is directly proportional to y, and this can be seen from this formula here. Acceleration is directly proportional to y. The second part is that the acceleration always points toward the direction of equilibrium position, and this is due to the negative sign here. So what does it imply from this diagram? From this diagram, you visualize that acceleration is going to increase, the magnitude of acceleration is going to increase as the amplitude, as the displacement increases. So we are going to have a maximal acceleration at this point when the displacement is going to be the amplitude. But now the negative sign is there to show that as the acceleration increases, it is always trying to point toward the direction of the equilibrium position. So at maximum acceleration here, you are always trying to point toward the direction of the equilibrium position. The equilibrium position is this line here. So now this is what the formula A is equal to negative omega squared y implies. So it's just going to be written as a simple harmonic motion is going to be negative kx, where x is your displacement. So now let's find now for the kinetic energy of the particles which are found in this which are used in the which vibrate in order to produce the wave. We know that W is equals to FdR. So the W is equals to Fr from classical mechanics, where F is a force moving in direction of the distance. So now we say that dW is going to be equals to Fdr. So now we know that if you want to have our kinetic energy is going to start at 0. We know that the displacement is going to be 0. At the kinetic energy Ke, we are going to have a displacement of y. So when we substitute now, we are going to have W, and when we are already integrate, we know that W from lower limit of 0 to kinetic energy is going to be equals to, we substitute the value of the force inside here, and the force is the force that is used in simple harmonic motion. Force in simple harmonic motion is going to be m omega squared r. This force is used because we said here that from the value of the acceleration, we can visualize that it is a simple harmonic motion which is occurring. So we can substitute m omega squared r from 0 to w, from 0 to y. So our kinetic energy is going to be half m omega squared y squared. So this is the value of our kinetic energy. Now, provided that you have a string which is moving, the potential energy that you are going to have is going to be the elastic potential energy. If you are producing the wave via using a string which can be expanded, the potential energy that is going to be produced is going to be the elastic potential energy. And so the force that is going to be the elastic force that is going to respect the Hooke's law. So when we integrate it from 0 to potential energy, we're going to integrate here from 0 to displacement y of the force which is the elastic force. And Hooke's law states that you are going to have the force is going to be a force exerted on an object is directly proportional to the extension, and that constant that is going to be produced is going to be the elastic constant, and it is provided that the elastic limit is not attained. This is Hooke's law. So you can substitute up to here, and you are going to have your final formula for potential energy to be equals to half ky squared. Now the maximal potential energy is going to be given as when the y is going to be equal to the amplitude, and that's half Ka squared, and the maximal kinetic energy is going to be when the displacement is going to be the amplitude, and that's half m omega squared a squared. And this maximal potential energy and kinetic energy are the maximal energy of the system. So now let's visualize longitudinal waves. In case of longitudinal wave, here the particles are going to vibrate now in the same direction, in the direction in which there is the motion of the wave. Particles are going to vibrate in direction with motion of the wave. So this is simply definition of longitudinal wave. So now let's visualize the formula involved with longitudinal wave. In case of longitudinal wave, since the particles are going to vibrate in similar direction to the wave, we are now going to consider the x coordinate of the wave and not the y coordinate. So here our x is going to be equal to, since this angle is still theta, our x now is going to be equal to a cos omega t. So this is a displacement function for the case when you have longitudinal wave, where waves are going to be vibrating in a direction of motion, where the wave particles are going to vibrate in the direction of motion of the wave. So now here the displacement is given as x is equal to a cos omega t. Now when you are going to differentiate now the velocity, when you are going to differentiate the displacement in order for you to have the velocity is going to be negative omega a sine omega t, and velocity can also be equal to negative omega a the square root of a squared minus x squared. Now the negative sign here shows that unlike with transverse wave, in cases of the longitudinal wave, the velocity always point in the direction, the velocity always point in the direction of the equilibrium position. And the sine omega t here shows that what? It shows that, so from here you visualize that you must have a displacement of 0. If you have a displacement of 0, then you are going to have the maximal velocity. So we see that what? You see that from this diagram, we realize that the particle that is going to be located here at the equilibrium position is going to have the maximal velocity. And now, as the velocity is decreasing, as you are going at the position where there's lesser velocity, the velocity is always going to point toward the direction of the equilibrium position. So now, this is the implication of the negative sign here. Every time you are going to see the negative sign on formulas, you are going to realize that is a negative sign on formula of simple harmonic motion. Then that negative sign will imply that the vector for that particular formula is going to always direct toward the equilibrium position. So here you are going to have the velocity vector, which is going to the velocity vector is going to be maximal when the displacement is 0, and the velocity vector is always going to point toward the direction of the equilibrium position. So now let's visualize now for the case of acceleration. Acceleration is found when you differentiate now the velocity above. So when you have differentiated the velocity above, you're going to have negative omega squared a cos omega t. So now when you have negative omega squared a cos omega t, you need to know that a cos omega t is similar to the displacement that has been found here. So we see that ax is going to be equal to negative omega squared x. So realize that the longitudinal wave also respect the simple harmonic motion. Now for the case of the kinetic energy is going to be equal to half m omega squared. So the kinetic energy is going to be half m omega squared x squared. The potential energy is going to be equal to half kx squared. So we have already found this kinetic energy and put elastic potential energy in the section above, but we've just substituted the x value instead of the y. So the total energy is going to be the kinetic energy plus the potential energy at the respective displacement. So now let's go to the next section, which is the classification of wave according to energy transfer. Now according to energy transfer, waves can be classified into two main parts, namely the progressive wave and the stationary wave. So now, what are progressive wave? Progressive wave are traveling wave which transmit energy and momentum as it travels in a medium. So now in this case, we need to know that the formula, this is a progressive wave. With this progressive wave here, you are going to see that it's a traveling wave, and you always have a delta x from the position with the phase difference with the traveling wave. So the general equation for this wave here is always going to be equals to y equals to a sine into omega t plus phi, and this phi with respect to this distance, this displacement distance graph, where you have a path difference of delta x here. We know that the lambda, this distance from here to here, is going to correspond to the angle of 2 pi, while delta x there here is going to correspond to the angle of phi. It implies that the phi that we speak about is only going to be the 2 pi delta x all over lambda. So we can substitute back in this equation, and we have the general equation for the displacement of the progressive wave to be equals to y equals to a sine into omega t plus 2 pi delta x all over lambda. And all this can be seen from the graph displacement against distance. In the first case, in the graph that we had above here, were the graph of displacement against time, and here was the graph of displacement against time. But in case where we are dealing with the classification of according to energy transfer, in order to speak about energy being transferred per unit distance, then we need to use the displacement against the distance graph. So now the energy of the wave is going to be given as a half big M omega squared A, and this is similar to the formula of energy of one particle, of the maximal energy of one particle, which is causing the wave. So now this one particle, in case the difference between the energy of the wave and the energy of the particle is this mass m here, in case above here, we've realized that energy of a particular particle is going to be half m omega squared x squared, and this m here is going to be the mass of the particle. But here in this case, the energy of the wave is not going to be only one particular distance. The energy of the wave is going to be when the displacement is going to be the amplitude, and this mass here is going to be the mass of all the particles in the system. So let's go again. Energy of the wave is with respect to the mass of all the particles of the system and the amplitude, while here the kinetic energy of the particle is with respect to only the mass of one particle and with respect to the displacement and not the amplitude. It's only the maximal kinetic energy which has the amplitude here, but the mass of the particle remains the same. So that's the difference between energy of the wave and the energy of particles. So now let's visualize the specific properties for a particular progressive wave. The specific properties are going to be shown from the formula of y is equals to a sine omega t plus phi. So now from this formula, we see that what? All particles of the wave within this cycle, so we have this cycle here, all particles within this cycle are going to vibrate out of phase. So all particles within this cycle, the cycle of the wave that is shown here, are going to vibrate out of phase. This is just because of the phase difference value here. Since we see phi here, then it implies that all particles are going to vibrate out of phase. The second specific property is that the amplitude does not vary with the phase difference. We see that here the amplitude is going to be a constant. So we realize that amplitude does not vary with phase difference, and it is similar for all the particles in the wave cycle. Amplitude does not vary with the phase difference, and it is similar for all the particles of the wave cycle. This is different in case of stationary wave. Again, progressive waves transmit energy from one point to another, and this is seen inside the definition of progressive wave, where it said to transmit energy with the net transfer. It causes a wave with a net transfer from one point to another in a certain medium. And lastly, the wavelength of the progressive wave is going to be distance between two particles which are in phase. So let's say that this particle is in phase with this other particle here. This distance from here to here is going to be the wavelength. So now let's visualize now the case of stationary wave. Stationary wave, these are waves whose particles have energy due to their vibration, but there is no net transfer of energy from one point to another. So the particles of this wave are going to have energy due to their vibration, but the energy transferred is going to be zero. So in this case of progressive wave, see that the energy is going to be the half m here, which is the total mass of all the particles in the system, omega squared amplitude of each particle. So amplitude of each particle squared. So now in this case of stationary waves, you see that there is no net transfer of particle. So there is no net transfer of energy. Since there is no net transfer of energy, then there will be a destructive interference. But before speaking about a destructive interference between two waves, we need to know what is interference, or what's the principle of superposition. The principle of superposition states that once two waves meet, the subsequent wave produced will be a summation of the displacement of the primary wave. So that's the principle of superposition, and this principle is going to help us to find for the equation of a stationary wave. So there exists two superposition. We have destructive superposition and we have constructive superposition. A destructive superposition, the secondary wave that is produced has a smaller amplitude, while in a constructive superposition, the secondary wave that is produced has a larger amplitude. But from the definition of stationary wave, we see that there is no net transfer of energy. So it implies that the wave that is going to be produced is going to be of destructive form. It's going to be due to a destructive interference. So the formula for the wave that is going to produce, for the displacement of the stationary wave, is going to be given as y is equals to y1 minus y2, where y1 is the displacement of the first wave and y2 is the displacement of the second wave. So now after having, so this is y1 is going to be equal to a1 sine omega 1t plus v1, and y2 is going to be a2 sine omega 2t plus v2. So these are y1 and y2 that we have. Now, what are the conditions? We have already seen now the principle of superposition with destructive interference occurring in case of stationary wave. So now let's visualize now the conditions for superposition to occur. Now, for superposition to occur, the wave must be of similar type. The first one is that the wave must be of similar type. That is, sound wave cannot superpose with light waves, but only with sound waves. Sound waves superpose with sound wave. Light wave superpose with light wave. Water ripple wave superpose with water ripple waves. So this is all what we are going to have. The wave must be of similar type before superposition can occur. The second case for superposition to occur is that the source emitting the two waves must be in phase. The source emitting the two waves y1 and y2 must be in phase, and the wave must have the same phase. That is, the wave must have the same phase difference. So it implies that this phi1 must be equals to phi2, which is equals to phi. Lastly, we need to know that the wavelength and the frequency of, for superposition to occur, the wavelength and the frequency of both waves must be similar. If the wavelength and the frequency of both waves are different, then the of the two waves which are superposing are different, then superposition will not occur. For superposition to occur, their frequency must be the same for the wave y1 and the wave y2. So now we know that frequency is found from the formula omega is equals to 2 pi f. Since their frequency f1 and f2 are similar, it implies that omega 1 is going to be omega 2. Now, also, for superposition to occur, the amplitude of both waves must be equivalent. So this amplitude A1 must be equivalent to the amplitude A2. So A1 is equals to A2 is equals to A. But this last principle of superposition is not always taken into consideration. The last principle of superposition of the year in this case is the amplitude of both waves must be similar. Is mostly taken when you want to do the superposition for the formation of stationary wave equation. So now we see that having taken these different conditions into practice, we see that now our equation of y1 is going to be equal to a sine omega t plus phi, and equation of y2 is going to be a sine omega t plus phi. So the angular velocity of the first wave is going to be equal to angular velocity of the second wave. The phase difference of the first wave is going to be the phase difference of the second wave, and the amplitude of the first wave is going to be equal to the amplitude of the second wave. So now we have y is equals to, we are going to use now the equation for destructive superposition, and that equation is because of the definition of stationary wave. We define stationary wave with not having a net transfer in energy. So it implies that the displacement, the superposition that has occurred is a destructive superposition. We are going to have y is equals to y1 minus y2. Since you have y is equals to y1 minus y2, you know that y1 is this and y2 is this. So we are going to subtract them. So we are going to end up by having a into sine omega t plus phi minus sine omega t plus phi. But in mathematics, we know that negative sine theta is equal to sine of negative theta. So this is in mathematics. So this now we can substitute now in this equation. So when we substitute back in this equation, we are going to have y is equal to a into sine omega t plus phi plus sine into omega t minus phi. So now, but also in mathematics, we know that sine A plus sine B is equal to 2 cos of A minus B divided by 2 sine of A minus A plus B divided by 2. Now we know that A in this case is going to be omega t plus phi, and B in this case is going to be omega t minus phi. When we substitute all these, we are going to calculate and end up by having this equation: 2a cos of 2 phi divided by 2 sine of 2 omega t divided by 2. So the last equation is going to be y is equal to 2a cos phi sine omega t. So now we see that the 2a cos phi is going to be the amplitude big A. So the formula of the displacement of a stationary wave is going to be written as y is equal to the amplitude, which is going to be 2a cos the phase difference sine omega t. Now from this formula of the stationary wave, we can now derive the different specific properties of stationary wave. Number one, the first property of stationary wave is that all particles of the wave in a loop are going to vibrate in phase. So we see that here the sine omega t does not have plus phi like in the case above here. In the case on the station of the progressive wave, we had a sine omega t plus phi. So all particles of that wave are going to have a different phase difference. So all of them are going to vibrate out of phase. So that is why here in this case of progressive wave, all particles are going to vibrate out of phase because they have different phase difference. But now in this case on stationary wave, the equation is written as such, so there is no addition of phi here. All the particles are going to vibrate with they have the same angle, which is 0. So all the particles are going to vibrate in phase. So that's the first specific property for stationary wave. Now from this formula, we realize that the amplitude is going to vary with the phase difference. This is because we can see here that amplitude is equal to 2a cos phi. So a is a function, is directly proportional to phi. So we realize that amplitude varies with the phase difference, is directly proportional to phase difference. But here we see that all the particles are going to, or in a loop are going to, so in this particular loop here, so this is a loop, all the particles in this loop are going to vibrate in phase, and their amplitude are going to vary with respect to their phase difference. So now let's visualize the next property. Progressive wave does not transmit energy from one point to another. So this is another we already know this from definition, that in case of stationary wave, instead stationary wave does not transmit energy from one point to another, while progressive wave are going to transmit energy from one point to another. So this is an error. The wavelength of the wave now is 2 times of the wave of this stationary wave is going to be 2 times the distance between 2 nodes, or 2 times the distance between 2 antinodes. So now let's come to this diagram again. These are the nodes here. So we can see here that these are the nodes and these are the antinode. So node. So the wavelength is going to be from here to here. So this is going to be 2 times the distance. This is one distance between 2 nodes. So it's going to be 2 times distance between nodes, or it's also going to be 2 times distance between antinodes. So these are different specific properties involved with stationary wave. So now let's visualize the next part, which is classification according to medium transfer. Now the classification according to medium transfer is going to be divided into 2 main types, which are mechanical wave and electromagnetic wave. Number 1 is mechanical wave. Mechanical waves are defined as waves which need a material medium for propagation. Example of this wave are going to be sound wave, even water wave. You need to know that sound, it can be transmitted in water, in air, and in solid. So sound needs a material medium for it to be transferred. Sound cannot be transferred in space. That is, if you speak to someone in space, the person is not going to hear you because there is no air in space in order to conduct the sound wave. Now let's visualize the formula involved with mechanical wave. The first quantities is going to be the speed, the second one is momentum, the third one is energy transfer, the fourth one is the power. Now the speed, the general formula for the speed of a wave is given as C is equals to F lambda, where F is going to be the frequency of the wave and lambda is going to be the wavelength of the wave. Now this is a general formula for the speed of all waves. Now the specific formula for speed of different waves can be written below here. We have point number 1, transverse wave of a string. The transverse wave of a string has a speed equals to the square root of the tension of that string divided by the linear density of that string, and the linear density is given as m all over the mass of that string divided by the length. So the speed of the transverse wave in a string is going to be equal to the square root of the tension of that string times the length divided by the mass of the string. Now sound wave propagated in gas or in air, we see here that the speed is going to be equal to the square root of this is going to be the gas constant. This is going to be a certain constant which has been found by Newton experimentally, gamma. P here is going to be the pressure all over the density. So speed is equal to the square root of Newton's constant, gamma, pressure divided by density. So now we know that from our formula density, we know that density equals to mass all over volume. When substituting in this equation, we are going to say that C is equal to the square root of gamma PV divided by M. So now let's visualize now. From here we know that the molar gas equation, so we initially had this formula, but we know that the molar gas equation PV is equals to nRT. We can substitute nR here. We're going to have gamma nRT divided by M. But we know that again, the number of moles which is found inside the equation of molar gas constant is going to be equal to mass all over molar mass. So here is going to be the mass and here is going to be normal moles. So I can place the molar mass equals to mass all over the number of moles. So it implies that the speed of sound in gas is also going to be equal to the square root of the gamma RT all over the molar mass of the gas. So these are the two equations here. Either you use C is equal to the square root of gamma P, pressure all over density of the gas, or you use speed is equal to the square root of omega R. Omega and R here is the molar gas constant, T here is the temperature divided by the molar mass of the gas. So now, but Newton has proved mostly that in air you are going to have gamma equals to 1.4. So the value of 1.4 is going to be used in this case when you are going to use air. So now let's find now for the speed of longitudinal wave in solid. The speed of longitudinal wave in solid is going to be given as example of these longitudinal waves is going to be sound. So when sound is going to be transmitted in solid, the speed is going to be given as C is equals to the square root of the Young modulus divided by density. Speed is going to be equals to the square root of the Young modulus divided by the density. So that's the value of speed. Speed is equals to the square root of Young modulus divided by density of the object and Young modulus of the object. So now let's find now the momentum transferred by mechanical wave. The momentum transferred by mechanical wave is just written as G, which is the momentum, is equals to the mass of all the particles in that wave times the speed, and the speed are the different formulae that have been found here, provided that there are these different waves which are involved. Now the energy transferred by a mechanical wave is given as E wave is equals to half m omega squared a squared, where we say that m is mass of particle, the mass of all the particles. So it's going to be the mass of each particle. So we sum all the masses of all the particles for us to have our m here. So this m here is normally supposed to be big M here, and is the mass of all the particles of the system involved in the wave transmission. Now the power is going to be equal to dE all over dt, but we know that m, omega and a are all constant in this equation. So now we need to multiply here. So you are going to have here that power is going to be equal to m omega squared a squared all over 2t. So we see that if we multiply the length above here and we divide by the length, nothing has changed in the equation. So now we know that L all over the time is going to be the velocity, and then the mass divided by the length is going to be the linear density. So the formula for power is given as half omega squared a squared linear density times the speed of the wave. And the speed of the wave has been calculated in the first section. Provided that and speed normally generally is given as frequency times the lambda. Now let's visualize the intensity of the wave. The intensity of the wave is normally given as power per unit area. Now we've already calculated the power to be equals to m omega squared a squared c all over 2l. Since we have calculated the power as such, we can substitute now in this equation. We have I is equals to, we substitute and place the area here. The area times the length is going to give you the volume. Now mass divided by volume is now no more going to give the linear density but the volume density, and that volume density is going to be represented as rho. So in this case, intensity is going to be equal to half omega squared a squared, the volume density times v. The difference between intensity formula and the power formula is that with power formula you have linear density, but with intensity formula you have the volume density. Now let's visualize the loudness. The loudness is also defined as the intensity level, and the formula for the intensity level of the loudness is going to be given as -10 log of I all over I0. So you have this formula here. So this is a formula for the loudness. So now we see that here this formula -10 log of I all over I0 is going to measure the loudness in decibels. So the loudness in decibels is going to be measured when you have 10 here. But now if you want to measure loudness in bells is going to be equal to loudness in decibels divided by 2, and that's going to be equal to the log of I all over I0. So now if I now interchange this formula, you see that this is going to be normally going to be negative, so I can bring this negative on the other side. Then I remove the I up here. I can bow it down to this formula here. I is equal to I0 10 raised to the power negative IL in bells. So now this is a formula that you can have. And now let's say that you have a case where the first intensity is given and the first intensity level is given, but you're asked to find for the second intensity when the second intensity level is given. So in order to do this, you're going to use this other equation in order to find it. The first equation in that case is intensity 1 I0 is the initial intensity of the object. I0 10 the initial intensity of the wave, I0 10 raised to the power negative ILB. This is equation 1 and this is going to be equation 2. If you divide equation 2 by equation 1, you're going to have the intensity 2 divided by the intensity 1, which is going to be equal to this divided by that. So your intensity 2 will be equal to intensity 1, which is known and has been given to you, 10 raised to the power negative L, 10 raised to the power negative IL, which is the intensity level of the second intensity, and you have 10 divided by 10 raised to the power negative 10 raised to the power negative intensity level of the first intensity. So here we have visualized the loudness. So now let's go now to visualize the electromagnetic wave. Electromagnetic waves are waves that are transmitted without any material medium. So electromagnetic wave does not require air or sound or water in order for it to be transmitted, because this is why the sun, which consists of light rays, is capable of penetrating and going onto the earth. We see that the sun is found in space, and in space there is no air. Since there is no air here, but we realize that the light from the sun arrives the earth's surface, it implies that the light ray can travel in a vacuum, indirectly or experimentally. So now let's visualize now the diagram of electromagnetic wave. Electromagnetic wave, from its name you can imply that it consists of both an electric field and a magnetic field vibrating perpendicularly as such in this diagram. So this is a diagram. So we see that so this is why electromagnetic wave, you need to know that electromagnetic wave are the only three-dimensional rays which are known. So this is why electromagnetic wave can be polarized to two dimensions. So now the condition of polarization states that in order for you to polarize electromagnetic wave, then it implies that what? It implies that the angle between the reflected ray and the refracted ray must be 90 degrees. So that's the condition for polarization. So polarization is visualized here. Here you have the incident ray, here you have the reflected ray. The angle between the incident ray and the reflected ray is going to be 90 degrees in case where the incident ray is going to be equal to angle of polarization. But we know that what? We know that from the law of reflection, when the incident ray strike with a normal located here, the reflected ray is going to do an angle which is similar to the angle done by the incident ray with the normal. So we say that I is going to be the angle of incidence is going to be the angle of reflection, according to the law of reflection. Now according to the law of, so it implies that I is equal to I here, or theta p is going to be equal to theta p here. Now according to law of refraction, we know that Snell's law states that what sine I all over sine r, from law of so from the law of Snell's law, or the law of refraction, we still need to know that the refractive index of that material in which it is penetrating is going to be equal to sine I all over sine r. But we initially said that what? We initially said that this angle, the angle between I and r here is going to be 90 degrees. So it implies that what? I plus r, so I plus r plus 90 is going to give you 90, is going to give you 180 degrees, and thus it will imply that I plus r is going to be equal to 90 degrees. Since I plus r is going to be equal to 90 degrees, r is going to be 90 degrees minus I. So from this formula in the law of reflection or Snell's law, in the law of refraction of Snell's law, we can substitute the value of r, which is 90 minus I, into here. We're going to have n is equal to sine I all over sine of 90 minus I. So now when you substitute, you are going to have refractive index equal to sine I all over cos I. Now sine all over cos is the tangent, so you see that the refractive index is going to be tan I. So the I is going to be the tan inverse of the refractive index, where the I is the angle of polarization. So it implies that our angle of polarization is going to be the tan inverse of the refractive index. So in order for you to polarize light such that it should be only in one plane, that is in two dimensions, you need to place the light at a certain angle of polarization to a certain medium, and that angle of polarization will be equal to the tan inverse of the refractive index of that medium from which you want to polarize. So now the formula quantity, so let's visualize the formula involved with electromagnetic wave. The main formula involved with electromagnetic wave is the speed of electromagnetic wave. The speed of electromagnetic wave, we already know that it's a constant in a vacuum, and that's 3.0 times 10 to the power 8, or more precisely 2.9998 times 10 to the power 8, and that's the maximal speed at which an object can attain. No object can surpass the speed of electromagnetic wave in the universe, according to the law of relativity of Einstein. So now this speed is going to be given as 1 all over mu times epsilon, and mu here is going to be the permeability of the space in which the speed is moving, and epsilon is going to be the permittivity of the space in which it is moving. where mu here is going to be the mu r, which is relative permeability times the permeability of free space, and here epsilon is going to be epsilon r epsilon 0, where epsilon r is going to be relative permittivity and epsilon 0 is the permittivity of free space. So here we have visualized all what is involved in waves. So we say thanks for your kind attention, and please don't forget to like and subscribe for Science Dream Makers. Thank you.